In this video, we're going to be looking at a single degree of freedom problem. And particularly for this example, we're going to look at two main sub-questions. As you can see, the question reads that we have a 269-meter tower, which is one of the towers that is found in South Africa, right, or Joburg, which is also considered to be the tallest tower in Africa, right? So it is also estimated that the diameter of that tower is about 30 meters, right? And that it weighs a mass of 4 times 10 to the power of 7 kgs, okay? And which is also evenly distributed throughout the tower, right? And then we are supplied with some additional information, as can be seen there. Particularly, we have the equivalent damping coefficient, the equivalent mass, and we also have the elastic modulus as well as the moment of inertia for that particular tower. Okay, so the first question asks, what will be the ratio of the lateral displacement of the tip of the tower in relation to the bottom of the tower if an earthquake hits Joburg at a frequency of 10 hertz? Okay, so let us look at the first part. Okay, so in the first part, we need to find the ratio of the lateral displacement. So the keywords to identify here is the ratio of the lateral displacement of the tip of the tower and the bottom of the tower. Okay, so we can assume, well, let's say let's probably say that the displacement of the tower at the top, let's say the displacement of the tower at the top, right? So let me write here the displacement at the top, right? Let that be denoted by x, okay? And the displacement at the bottom, okay? Because we're also given that it's at the bottom. At the bottom is a value. Let's just assign it a letter y. Okay, so what we are interested in finding as per the question is we are want to find what is the ratio of these displacements, right? What is the ratio of the tip of the tower versus the bottom of the tower, the displacements. So we want to find the ratio of those displacements. Does this ratio ring a bell? Of course it does, because this ratio is the ratio for the transmissibility. Okay, so if I can just scroll up to the problem, what we have learned so far in the theory, if you still recall, for single degrees of freedom, we have what we call transmissibility, right? Which in this case is the ratio of the displacement of the top or the tip of the tower versus the ratio versus the displacement of its base. So let's take, for example, maybe just to digress a little bit, okay? So let's say, for example, we have a building, right? We have a building that is entrenched in the foundation, right? As an engineer, ideally you would want the building to be designed in such a way that if we have an earthquake, right? Let's say that earthquake is going to cause the ground to have a displacement y, let's say the ground's displacement. So remember, earthquake, they're gonna cause some tremors, either be it up and down or swerving from left to right. Okay, so let's say that foundational displacement is, for illustration purposes, is of magnitude, let's say 10, right? Let's say let's just say, for example, it's only 10 meters, right? This is the displacement of the foundation or the ground, right? Ideally, the people who designed this building would have designed it in such a way that they want the building to, the tip of the building, they don't want the building to be swerving from left to right. They don't want the building to swerve too much, right? So ideally you would want the building to have a minimum as much as possible in terms of its displacement. Okay, so ideally you would want a building to swerve, let's say, if the foundation has been displaced by 10 meters, ideally you'd want the building to displace by, let's say, for example, let's say 5 meters. Okay, so this is much better, unlike a scenario, let's say, where we have a building which the foundation has been displaced by 10 meters, and then we find that our building is being displaced by a value, let's say 15. This is not a good design, right? Because we want our building ideally to be able to dampen that displacement due to the base excitation of the foundation, right? So we want our building to have some properties that are going to, in actual fact, that are going to suppress the displacement due to the earthquake. So ideally, we would want the building to have a much lesser displacement. Okay, so that was the illustration that I wanted to just quickly show you before we go back to our question again. Okay, now going back to the question. Okay, if I can just scroll down. Going back to the question, we remember, like I have said, this ratio is the ratio which we call the transmissibility ratio. Okay, so the ratio of the displacement of the base and the response of our system, particularly in this case, which is a building, is the transmissibility. And we know that for the transmissibility, it is given by the general equation, which is square root of 1 plus bracket 2 zeta, right? This is zeta, it's not a c, r squared, okay, all over bracket again 1 minus r squared, also squared here, plus 2 zeta r, 2 zeta r, okay, 2 zeta r squared. Okay, so this is based on the theory that we have learned so far about transmissibility. So like I've said, this is the transmissibility, right? So it's just basically the ratio of the displacement. In this case, the displacement of the earthquake is the one that is causing the excitation of the building. And in response, the building is going to move by a certain displacement, which we have attributed in this case as x. Okay, so basically this is what we want to find according to the question. What will the ratio of the lateral displacement of the tip of the tower be? Okay, so that's what we want to find. Okay, so now what is only left for us to do is to find out what is zeta. So we need to find what is zeta, right? We need to find what is r, right? Because if we can find them in this particular equation, which I'll call equation number 1, right? In equation number 1, what we can then do, if we have zeta and r, then we are able to solve for the first part of the equation, which is the ratio of the displacements. Okay, so let's get right into it. Okay, so let's start first with, for example, we can start with zeta. Okay, so what do we know about zeta from theory, right? So we know that the formula to find zeta, right? So we know that zeta is the ratio between the damping coefficients. So it's a ratio between the damping coefficient of the particular system divided by its critical damping coefficient, right? So in order for us to find find zeta, we need to find the ratio of the damping coefficient, which is given here, versus its critical damping coefficient. So we also need to account for that. So we know that, if I can just highlight this, so we know that the damping coefficient, this we do have, right? But we don't have the critical damping ratio. So we must go on and find what is the critical damping ratio. Okay, so what I'm going to do, I'm just going to box it here. Okay, so what do we know about the formula for the critical damping coefficient? So the formula for the critical damping coefficient is given as 2 root of K over M, Km, okay? Where K is remember K is the stiffness, right? As well as M is the mass of the system, okay? So we also realize that, so the reason why I'm working it out like this is I want you to understand the notion, how we go about to solve some of these problems, right? So based on the given information, well, we can see that we have the equivalent mass. Okay, so remember in this particular case, we are working with equivalent mass and we are also working with equivalent stiffness, right? So we see that already we have the equivalent mass. That is not a problem. The problem comes when we don't have a K, we don't have the given stiffness. If you are to look at what we do have here on the given information, right? What we do have is we are given all the other information, but we haven't been told what is the K, and K in this case is the stiffness. Okay, so we are seeing that we are doing back calculation. Then once we get all those back calculations, we're just going to start feeding them back into our problem and solving it as a whole. Okay, so now we are also now going to be tasked to find what is the K equivalent. Okay, so in this particular case, how do we go about to find K equivalent? How do we go about to find K equivalent? Okay, so remember one thing. If you still recall that sketch that I drew, trying to sort of like represent the problem in a picture, what I did have is I had a building, right? I had a building that was rooted to the foundation, right? So if you look at this system, right, what sort of structural resemblance does it look like? So we have a building that is fixed to the ground. So the way I can see this is a cantilever beam, right? I can see that this is actually mimicking a cantilever beam, right? So this is a cantilever beam, right? So the reason why we need this information is because if you look at the different structural tables, what you will see is for the different orientations, be it a cantilever beam, a simply supported beam, we do have different K equivalents that are associated with the different structural orientation. Okay, and if you look in the tables for a cantilever beam, what you are going to see is that the stiffness that is associated with the cantilever beam, right? The stiffness that is associated with the cantilever, right, is equal to 3 multiplied by the elastic modulus multiplied by I, which is the moment of inertia, all of that divided by the length to the power of 3. Okay, so this is how we go about to find K. And if you substitute in, remember, E we are given from the question, we are given E, which is 30 gigapascals, and we are also given I as the formulation. And remember, if you read the question, we also have the diameter given and so forth. Okay, so what I'm going to do is I'm just going to write down the final answer. So if you substitute in the value of E, this value of I, right, and the value of L, what you are going to get, or maybe let me write it in full so that you can follow. So it's going to be 3 times 30 gigapascals, which is going to be 30 times 10 to the power of 9. Okay, so 30 times 10 to the power of 9 multiplied by your I. So if you calculate your I using this particular formulation here, right? If you calculate your I using that particular formulation, what you are then going to get for your I value is going to be that your I value is going to be a value that is of 300. So if I can write it, so it's going to be a value of 300, 3, 9, 760. Okay, 0.74. Okay, all of that divided by the length. Remember the length of the building, which was given as, in this particular case, 269. Okay, so if I can just zoom out so that you also follow as I write here. So 269 cubed. Okay, so now what we then get is our K value. You're going to see that our K value is going to be a value of, it's quite a big value, so 183,840,234. Remember, newtons per meter. Okay, so this is Newton per meter. Okay, so now that we have gotten our K equivalent, right? So now that we have gotten our K equivalent, we can now go back and solve for the critical damping coefficient. So if we now substitute in the K equivalent, which we have just solved, and the M equivalent, which is given in the question as 33 over 140 multiplied by the M that is given in the question. If you do so, what you get as your critical damping coefficient is a value of 26. It's a value, sorry, it's actually a value of 832,670,57. Okay, so that's the value that you get. Okay, so if I can just clean up, just erase this, since it's no longer relevant based on what we have just, you can always rewind and just try and understand what you're going, or feel free to also leave your comments in the comment section, and I'll gladly attend to the questions that you might have. Okay, so now we have our critical damping coefficient. We can now also go back. So if I can just, we can now go back and also solve for zeta, right? So using the values, so let me just keep the same color. Using the values that we have just found for the critical and the given damping coefficient value, what you are going to therefore see is that the value that you get for your zeta, right, if you are to plug in the damping coefficient, which is given in the question here, and the critical one that we just found, what you will get is you're going to get a zeta value of 0.7206. Okay, so we have found one aspect of our question, which is the zeta part, right? So we have found the zeta part. Now all that is left is to find what is R, right? So if we find what R is, we can go back to equation 1, substituting the value of zeta and R, and then out pops our value for the ratio. Okay, so R, what is R? So we know that R is the ratio of the frequencies, right? So in this case, R is the ratio between the frequencies, which is in this case the natural frequency, and the excitation frequency. Okay, so how do we go about to find those? Okay, well, we first need to find what is the, we need to find what is the ratio, what is the excitation frequency according to the question, and we also need to find what is the natural frequency. So based from the question, we can see that the excitation frequency was stipulated. If I can zoom in, you can see that the excitation frequency was given in the question. If I can just erase everything else so that you don't, you can clearly see where I'm pointing at. The excitation frequency was given as 10 hertz. Okay, so if we convert 10 hertz to radians, that is going to be equal to 62 radians, approximately 62 radians per second. Okay, so that is given the excitation. But what is omega n? What is the natural frequency? Well, for the natural frequency, we have to solve for it individually. So we know that the natural frequency is given by the formulation that K over M. And remember, in this case, we are working with equivalence, right? We are working with equivalence, right? So we have already calculated what K equivalent is, what M equivalent is. So all that is left now is to solve for omega n. And if you do that, what you do get as your value for omega n is a value of 4.41568 radians per second. Okay, so I'll just come here and then plug in that value. That is 4.41568. Okay, so that is the value for the natural frequency. Okay, so if I can just quickly erase this small calculation for the natural frequency so that I can have space. So it seems like we are making progress. Okay, it seems like we are making progress. So we now have determined what zeta is. We now have the value of what we have zeta, we have r. So now means to say that if we go back, so if we now say substitute, right, we can now say substitute the value of zeta and r in equation 1. Okay, so we now need to solve for that ratio. And what you realize, if I substitute in equation 1, what I then get is that x over y, right, is going to be a ratio of 0.1014. Okay, so this will be my answer for the first part of the question. What is the ratio of that, the ratio of the movement of the tip of the tower in relation to the bottom of the tower? Okay, so that is the first part of the question. Okay, that is the first part. Now, let's have a look at the second part of the question. So what I would do is the second part of this question, I'm gonna do it in the next video, so that at least I can have some space to work it out nicely. So join me in the next video as I do part B of this question.